Now, this starting this section is a branch of statistics known as inferential statistics, meaning that we are using sample data to try to approximate the population value. And that's very commonly done in statistics. Because in just a lot of cases, it's just not possible to collect the entire population for data. You know, if you were trying to find, you know, the average male height in the United States, I don't think it's very feasible that you could actually collect all that data. So we use samples to make our best educated guesses on these things. So it's very educated guessing, but it's in a way, it's sort of, it's kind of guessing because you're using samples. Now, we're only doing the mean in this class, but excuse me, you know, if there was a second part to this class or something, we would probably do standard deviation and variance. Where, so this, you know, this case, we're going to be using the sample mean to approximate the population mean. So you're using sample statistics to estimate the population parameter. Now, the most basic way you can do it is what's called a point estimate, where you just kind of come up with a single number. Let's say you take a group of data and, you know, you would average that. And we claim, you know, that's our representation of the population parameter. We're not going to worry about getting into this term in this class, but this term unbiased is actually a statistics term, not biased in the sense that you would think of the word biased. It's technically the most mathematically unbiased, you know, so if I put that word in front of it, that probably would have clarified that it was something different. So that's one way you can do it. Now, another way that's very popular, and that's what we're studying now, is interval estimate. Is the interval or range of values that you use to estimate a population parameter. Now, an interval estimate is going to contain a range of numbers, so you've got a much more likely chance that your value will be in that interval versus trying to guess it with just a single number. If you're trying to guess it with a single number, you know, you might be high, you might be low, you know, it's hard to tell. But interval gives you a better chance. Now, of course, we're going to see how to construct these. And you're going to love this stuff because it's pretty calculator friendly. All right. So for this data, the point estimate here is the sample mean. Now we have this left endpoint and this right endpoint. And, you know, we'll see how this is actually calculated. We don't have enough information to make the calculation of how it comes about. But they are the same distance away from the middle. It's symmetrical. So this one, and the distance from the center to each endpoint is called the margin of error. And it's a distance of 2.1. So our interval estimate can be written one of two ways. It can be written in parentheses, or the population mean symbol saying that we're between 10.3 and 14.5. Now, we're not doing proportions in this class, which we might have done with, you know, with a second class of this or whatever, but you see these, you'll see proportions. Now, they won't actually give you the interval estimate, but you'll see they'll give an approximation, like an election or something like that, predicting an election. Then you'll see in small print there with a margin of error of plus and minus, you know, 3%, that sort of thing. That's basically this idea right here. It's just used for proportions. Okay. So let's see. Now this next term, the level of confidence is the probability, C is the probability that the interval estimate contains the population parameter. Okay. Now, we're not so concerned with this being, 100%, because you can guarantee something's 100% if you want to, but a lot of times it really wouldn't be relevant information. Like if I was going back to the example of the male height. Well, I could say with 100% certainty that the average male height is somewhere between 2 feet tall and 10 feet tall. I could pretty much say that with absolute certainty. But that's not really useful information, is it? Even if it's 100%, who cares? That big deal. Or just with any kind of real numbers, forget that example, but you could say, hey, well, I know it's somewhere between negative infinity and infinity. Yeah, that would be true, but not helpful. Okay. So we're willing to give up a little bit of the percentage there to have a more meaningful answer. Now we got, confidence levels. They don't certainly be these 3 numbers only, but common values are 90%, 95%, and 99%. So if you do a 95% confidence interval, what that means is when you're done is that there's a 95% chance that your population mean was in that interval, which means there's a 5% chance that it wasn't. But you'll never know that, so you don't have to lose any sleep over it. You can't control that. Now, this little graphic on the right, you're not going to have to be worried about constructing anything like this, but let me show it to you. Okay. And also with this one's a 90% right here. Now, when we say another thing that also means that in addition to 95%, this means if you took every possible sample from a population, 90% of them are going to contain your mean. So this is just showing that they collected 10 samples. Now, that doesn't mean if you collect 10 that for sure 9 will be right and one won't be right. You remember something we talked about in probability not too long ago, the law of large numbers? Sort of like that, it just means, over the long haul, over all calculations, it's going to be 90% of them are going to be in there. But this way is just showing you that what they've done is that the black dot represents the sample mean for that particular group. So these are all different samples taken from that same population. And the dot represents, and then the lines represent the margin of error. So the whole width, that's the entire interval, all the way across. The margin of error is going to be the same for all of those. We'll talk about that in a little bit. But this was 10 of them. But notice the third one. That's what's just trying to show you. And then suppose somehow later that, a lot of times you're not going to know this, but so hypothetically that we found out that the population mean was that value on the x-axis where that pink line is. Notice that third one does not overlap that line. So that's just showing you an example of a confidence interval where the population mean did not fit in that interval. Like I said, it didn't mean anything was wrong. You just happened to collect some data, that where it didn't, maybe it was kind of skewed one way or the other to where it didn't calculate to where it overlapped what the population mean really was. So, maybe going back to the height thing or something, you might have collected data that happened to be a group of really, really tall people or something like that. Of course, that graph would have been to the right of the mean, but it could have missed the mean. So essentially, the construction of a confidence interval is going to be taking your sample mean. This capital E represents margin of error. So it's your confidence interval. It's your sample mean minus the margin of error, and then the sample mean plus the margin of error. So the sample mean is always right in the middle of it, as these dots indicate right here. And then both directions are the amount E. I'll just draw it on one of them here. Like that's E right there. So what it's worth, then the entire width of the confidence interval is 2 times E. E plus E to E. Okay. That's the entire width. Okay. Now, suppose that you were just given a confidence interval with this two numbers like here. I like to put this problem on the third exam. So we'll pay careful attention to this one, along with many other delightful problems. But this one I traditionally put on there. Can't imagine why I wouldn't. So suppose you were just given this confidence interval. We don't know anything yet about the percentage or blah, 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 you know, because we're going to be calculating confidence intervals when we have data presented to us here shortly. But let's say this is all you know, 33.2 to 47.6. From that information, can you find X bar, which is the sample mean, and can you find the margin of error, E? And guess what? You can. The margin of error is always right in the middle. So all you have to do is add the two numbers together and divide by 2. It's that easy. You add the numbers together and divide by 2. So it would be 40.4. Now here's how you can calculate the margin of error, and I'm going to verbally tell you another way to do it after looking at it this way, and you can just choose whatever you want to do. One way to do it is, because it's the same distance from the mean to either end, is just subtract. You know, you can take the 40.4 and subtract the low number, get 77.2. You don't need to do this twice. You do it once, you got it. 47.6 minus 40.4. You get 7.2. Another way to do this is, because the entire width of this thing is 2 times E, like I mentioned a minute ago, is if you subtract those two numbers and divide by 2, that will also get you the 7.2. Just another way to do it. I mean, it's not hard to do. I didn't think I need to come up with too many ways to do it, but I feel like I'm cheating you if I don't at least tell you that, you know, so subtract and divide by 2. Okay. Now here comes, we start using some statistical formulas. Okay. How we calculate the margin of error. Oh, and I forgot to mention, this section is based on the population standard deviation is known. So we're going to be, it's either going to say population standard deviation, or it's going to show the little sigma symbol, you know, right there, the O with the hook. Because it's going to be a different calculation in the next section if we have the sample size instead of the population standard deviation. Now, even though the population standard deviation says it's known, it could be more, it could still be estimated, but you don't have to worry about that. Just got to tell you which population, which standard deviation is being used, whether it's population or sample. This section is all population. So this Z alpha over 2, that's going to, you know, it's got Z there, so you can bet that's probably going to be something on the normal curve or normal curve chart. See, that didn't go away just because the second test ended. It's still around. Well, actually, it wasn't going to go away anyway, because we still have it for those two other sections. So yeah, it wouldn't. I forgot about that. Yeah, I'm thinking the way this course used to be taught. But yeah, it's still going to be relevant, obviously, to the next exam because of the other two sections from last week. We got to talk about how to get this Z. And I'm going to show you technology-wise how to do it pretty easily, but I'm going to explain it conceptually for those that need to know how to do it that way. But you will be able to use technology for this. So it's going to be whatever this Z value is times the given population standard deviation divided by the square root of n, where n is going to be whatever the sample size is. So those two numbers are going to be given. Now, the confidence, the Z won't necessarily be given, but it gives you the confidence level, and you can get the z-value from that confidence level. And you'll also be given the sample mean. But let's take a look at conceptually how this works. I guess I might as well go to the notes here for a second and bring up that chart. And I might as well bring up the next chart. Oh, wait. Charts. Is that still, maybe I hadn't moved these over yet from, oh, there it is. So let me bring up the cumulative normal, have that here. And then I'm going to bring up this next one. And did that not open up? Oh, there we go. And let's bring up this other one. All right. So we'll come back to those PDF files. All right, tremendous. Yeah, we're going to need this t distribution here in a minute too. Okay. Now, unlike percentiles, so we have to make sure we distinguish this idea from percentiles, which is, that's on your next test also, because it wasn't on the last one. That's the part 3 from the normal distribution. Percentiles always means area to the left. Now, for these confidence intervals, I mentioned that's what these are called, confidence intervals. Yeah, I forgot to maybe define that, but they're confidence intervals is the name of this. Sorry about that, but I'm sure you knew that anyway. So I might not have actually said confidence interval, but you'll hear me say it enough. So, but anyway, that always represents a middle amount of area. It's not one way like percentile. It represents a middle amount. So if someone was using a chart to do this, you would think of 95% being a middle amount of 95%, not strictly left like a percentile. So what we would do, and I've kind of shortcutted it with this little inverse. I mean, even people using a chart can still use they don't use the inverse norm, but they use that 1 plus CL over 2 is very helpful. That makes it easier for everybody. But anyway, the way to rationalize this is if 95% is in the middle, I need that piece on the left right there to add it together to convert it to a percentile. Because if I'm going to find that z-value that's circled right there, I need the entire area to the left. So basically, if you've got 95% in the middle, you've got 5% total left. Everything is perfectly symmetrical. So half of that would basically be 2.5%. So as a 0.025 is 2.5%. So you add that to the 95 and you get 0.975. So what we have done, we've converted 95% confidence level to 0.975 percentile. But the quick way to come up with that percentile number is just take 1 plus your confidence level all divided by 2. So make sure you either use parentheses, or if you hit 1 plus that number and hit enter, then divide by 2, that would work. Because I've had people in the past, especially like in face-to-face classes, they'll be doing that. I'm not getting the right number. And every time, because they're doing something like, good time to wake up the calculator. Well, I'll just say what it would be. But if you just typed in 1 plus 0.95 divided by 2 with no parentheses or anything, you're going to get, I think, 1.475, I believe. So I wonder why they were getting it wrong every time. That is why. And 0.975 just, happens to be directly on the chart. It's in the 1.9 row and the 0.06 column. I can't wait till this thing warms up so I can minimize it. Get it out of the way. All right. I don't need to type that in there. I know that's what it's going to equal. So, well, we're going to be needing this pretty soon anyway, obviously, to do confidence intervals. So I'll show you the next example in the calculator. But there, I've got it. Okay, yeah. But if you use the inverse norm command directly, and I'll show you, you just would put in. Well, another thing is if you can tell that 1 plus 0.95 is just 1.95, you don't have to mess with all those parentheses. But the inverse norm will give it to you, but after you've converted it, though, because remember, these aren't percentiles like they were before. Percentile, you just put inverse norm, whatever the number is. Here we have to get it to this number. We have to convert it from confidence level to percentile. Then it gives you exactly what we need. Okay. And I'll do this I'll do this one in the calculator. And I tend to ask one of these on a test too. What's the critical value? Just make up some random percentage, 82%. So all you got to do is the inverse norm of 1 plus 0.82 divided by 2, which is 0.91. So I'm just showing you 8 2s in the middle and then 0.09s at the end. And if you were using the chart, you would look for the closest one to 0.91 and you get 1.34. So the inverse norm I showed you right up here is kind of, we know what the 83 is going to look like, or some of the more basic 84s. So we'll take a look at it from the more, updated, which we've seen this before. So it shouldn't be too. So you can just go 1 plus 0.82 divided by 2. Left. Now, there it is, 1.34. Now, this one, you can only do it on this kind of calculator. Maybe I shouldn't show you this. I don't want to confuse you, but you can ignore this. But those using the 83 won't be able to do what I'm about to do here. But I feel like I should show you that feature because it's there. But you can just stick with what I just did and it'll work every time. I'm going to clear that out. If you put in 0.82, but change this to center, well, it gives you that negative side. You don't need the negative side. You just need the positive side. I don't know. I hope I didn't freak you out there or whatever. But, I don't know if you want to use that or not. Because one good reason not to use it is because on a test, I don't know, the order of the problems, how they're going to appear. Because especially when you're doing a percentile, you might want this to stay left all the time, in other words. So that way you don't do a percentile problem and forget to change that from center back to left. That's the disadvantage. Doing it the first way I showed you might be the way to go, because that way you keep that in the left position at all time. But somebody asked me about that one time, I remember, so I felt obliged to show it. There's where we were before. Wait, I must have typed something in wrong there. Oh, I forgot to divide by 2. 1.82 divided by 2, which is the first one we did. Second, insert 0. Okay, there we go. Yeah, so I don't know. I just want to show you that, but you can pretend like I never said it. And there we go. Now, this thing called the t-distribution is something we're going to talk more about in the next section. But this chart I kind of took and I combined it to where it'll help us with this section and then also the next section. Well, actually, it's probably not going to matter too much if you're using the calculator to do your confidence intervals anyway, but for somebody that was using the confidence interval formula, this will come in handy. But this T-chart will come in more handy the next section. Let me come back over to the PDF files here. Bring up, yeah. Now these, so somebody that was doing this, with just a regular calculator, this could come in handy. This is the T distribution, but we'll talk more about that later. But it's the Z distribution, which is what we're doing right now. Everything in this section would come from that top row. So you see this is only for a few select confidence intervals: 50, 80, 90, 95, 98, 99. I can't imagine anybody even wanting to do a 50% confidence interval. That's why bother? That just says you got a 50% chance of being right. That's not very good. All right. But then here are the values. You see, this one's the one we found earlier. I showed you with 1.96. I actually showed how that was calculated. But somebody that was doing these then for any of these confidence levels would not need to figure out that number. They would be able just to get it off of here. Then all this other stuff's going to come into play in the next half. Okay. After halftime. Oh, right. I got so excited about the next half, I opened up those notes. All right. Okay, so I'm just mentioning the top row, infinity. All right, so here's the actual official formula for anybody that does need it. Any confidence interval starts out with X bar, plus and minus, and then we've talked about that's the margin of error part right there. It's that critical Z value times your standard deviation divided by square root of n. Now notice, even though this says plus minus, in an interval, the lowest number is always written first. When you write any interval, you always see the lowest number first. So in reality, this would be expressed with the minus one first and then the plus one there. I didn't explain what that alpha over 2 meant. I guess I could. You don't have to really know it, but you want me to, I can go back up to that graph and tell you. The alpha over 2 is the piece of area that's, well, I kind of wrote it right there. It's that little piece right out here. So this little piece of alpha over 2, that means the rest of it's the area to the left. So that's just a symbol that you don't have to worry. It's not like it's going to be a different symbol in some problems where you got to know how to distinguish it. No, that's just the definition of it. It's just kind of there. It's not anything you have to. Some books use C for critical value. They'll just use a ZC or whatever. So it doesn't matter. Now here's one kind of done manually. All right, 35 days. Population standard deviation. So that's our clue that it's this section. Like I said, it's either got to say the word population or have that little population standard deviation symbol. And then we know it'll be this section. If not, it'll be the next section. And it's 35. And then here's the formula, 35 days. They want the 90 and the 95% confidence intervals. Which one is wider? Wider meaning, of course, farthest apart. Contains more numbers. All right, so here's the formula. Somebody was doing it this way. You take the mean, 23.20, plus and minus 1.645. Oh, 1.645. That's one of the ones that's on the chart. 90% right there. So someone doing it by this method, they wouldn't have to do the inverse norm thing. or even the table lookup, because they can get it right from there. Okay. All right. Times the standard deviation 1.645. Standard deviation of 4.34 divided by square root of 35. And you get an interval of 21.99 to 24.41. So what that's saying is the average stock price, closing price for Hasbro for the year, there's a 90% chance it's between 21.99 and 24.41. Which I guess in this kind of situation, you could probably actually collect all of that data pretty easily, but let's just pretend like it would be difficult, but I don't think it'd be that difficult. But hypothetically, let's just say, now you ready to see how I do this in the calculator? Let the games begin. All right. Stat. I'm going to use a new one here now. We've used calc, and we've used second distribution, for the binomial, normal, all that stuff. Test. We're going to be using 1 and 2 and 7 and 8. 1 and 2 in the next chapter. Number 7, we are a z interval. The next section will be the ones that are the t interval. So when the population standard deviation is known, it will always be a z interval. If it's unknown, it'll be a t interval. That's the difference. All right, data would mean, we're going to see some ones with data in the next section, but not for these. Stats means, data means it's taking data that you've entered and figuring out the mean and standard deviation. But that's not necessary here. We have that information. So we go to stats, hit enter. It means we're going to type in the information. Let's see if I can do this off memory. 4.34. 2320 maybe? Let me look.
Yeah, it is.
Yeah, there we go. Should have trusted myself. 2320, thank you. Oh, brain fart here. N is 35. And the confidence level, you enter it as a decimal. Now it's 0.90. Don't freak out when you move the cursor and the 0 goes away. That's all right. Still 0.9. So then you hit calculate. There it is. 21.99 to 24.41. Isn't that exciting? I knew it would be. And there it is. I don't know if this looks, trying to remember. This may not look that much difference between the two kinds of calculators. I don't want to, that's what I'm saying might. I don't want to speak and be wrong, but this might be one of the few things where it's not totally different looking. Now, let me do it real quick while I'm here, and I'll do it for 95. So it's stat. And the only thing, see, the calculator's figuring out that z value, internally, so we don't have to even tell it that. This one's going to be 1.96, but we don't, it'll figure it out. So now I just put in 0.95. But I got a feeling the calculators might be kind of similar. Whereas the others, we saw some differences. Okay. But yeah, somebody doing this manually, the only difference is that Z changed to 1.96, room to 95. Right there. But that wasn't your concern if you're doing it this way, so. A lot of people after we start doing this, they sometimes find this a little easier than the normal distribution, just for the sake of you're not worrying. So you don't worry about direction on this one. It's not left, right, middle. It's only middle. So the calculation, you don't have to even think about that. It's always calculating the same thing. You're not, oh, is this less than or is this greater than? Or now, which one is wider? That's measuring the distances between the two. The 95% is wider. And actually, I could have answered that question, but I wanted to wait until the end. And now you'll be able to. End of the problem is that question could have been answered before we even put one number in there. Because the higher the confidence level, the wider the confidence interval is going to be. Now, it kind of makes sense logically if you think about it. If you don't want to think about it logically, that's okay too. But let me explain why it kind of makes sense. Because remember the percentage is the probability that your population mean is actually in your interval. So if you increase that probability and make it higher, it needs to include more numbers to cover. It needs to have a bigger range of numbers to cover to make it more likely. That's the reason why. Yeah, so like I said, you can always make any confidence interval 100%, but your answer would be kind of useless. You're trying to get the highest percentage you can get and still present the information as relevant as possible. As budding young future statisticians that you are, that'll be your choice to decide. So when it's trading a little bit of precision for a little bit of accuracy, in other words. So if you were 95 is a pretty common one to use or whatever. So, in other words, do you go up a little bit to include more numbers, or do you want it to be narrowed down a little bit to be more containing, it's a little smaller range? Good news is that's not your problem in this class. Your problem is to answer the question in front of you. All right. Okay. Let's see. So, and I've been known to ask this as a word type question on a test. So, and I wrote these together, meaning they work together. In other words, this one, increase goes with increase, decrease goes with decrease. So if you increase the confidence level, you'll increase the width of the interval. If you decrease the confidence level, you'll decrease the width. And decreasing the width is also known as improving the precision or whatever. I mean, I won't ask it that way on a test, but that's what it is. All right. Now, sample size has the opposite effect. Now, I'm mentioning here the when you're affecting the width of a confidence interval, the sample mean has nothing to do with this, because remember, the sample mean maybe has everything to do with what your confidence interval is going to be, but has nothing to do with the width, because your confidence interval is just a fixed point value that sits right in the middle of it. It's the margin of error that stretches it out and makes the width. So that's what we mean. So that's why I don't have the sample mean there anywhere, because it has nothing to do with the width. That might be a good choice. I could answer on that. Put on that, on that test. I could put only the sample mean affects the confidence interval or something like that, which would be completely wrong. It affects the width of the interval. That would be completely wrong. Has no effect. Now, so you can affect it by the confidence level you choose. Now, I'm going to assume, since the standard deviation is a calculated value, you can't just randomly change that, but you can change your sample size. If you're collecting data I mean, you might be able to change your sample size. You might be able to collect more data and affect it that way. So you see that since this n is in the denominator of the fraction, anytime you increase the denominator of a fraction, the fraction gets smaller. So that's why if you increase the sample size, you'll decrease the width of the interval. So they have opposite effects on each other. So let's say if you wanted to do a 95% determine, to do a 95% confidence interval, but you want to increase the precision, in other words, without lowering the confidence level, you want to increase the precision, in other words, narrow down the interval, you could do it by increasing the sample size. Instead of collecting 100 pieces of data, you could try to see if you could raise it to 150. That's one way it could be done. I mean, well, that's the best way it can be done. This is kind of the general rule of thumb when you're doing inferential statistics is the larger the sample size, the better the results, more you can trust them more. Okay. All right, so let's try all right, National Football League players, average weight of 252.5. Assume the population standard deviation for the weight of all players in the league is 31.1 pounds. Determine the 80% confidence interval for this sample. So the first three numbers in blue are just copied right from the problem. Notice it says population standard deviation. 80% for somebody using the chart. If you're not using the chart, you don't have to get that number. Now keep in mind what I do on a test though is, for these you don't have to get the number, but everybody will need to be able to get the number for like this kind of example right here, where it's not on the chart at all. So even though, so if you're using a calculator to get confidence intervals, that's fine. But keep in mind, you will need to know how to do this once on a test. But to do a regular confidence interval, no, you don't have to worry about coming up with that number. You can let the calculator do it internally. I think I'll just skip the entry process on this one since we're about to get to the homework in just a second. You'll see me do it there. But so there I've got it typed in, set up in the formula. And then here it is entered in, all the information's entered into the Z interval process. And there it is, 246.97, 258.03. There we go. Okay, this is even another way you can write confidence intervals. And I don't use it the formula much, but something to something, that's okay. I think some of the homeworks do stuff where they'll just fill in blood. They say upper value, lower value. You got to be careful though. I think sometimes they put the upper value first when they're prompting you. That's okay. But anytime that you were looking at answers like this on a test or something, you're always going to see the lower number first. So just, look at it. I'm just saying in my math lab problem, the first question might ask upper value. So you would actually put 98.74 first. Okay, that's pretty straightforward here. 99%, that's a new one. That's right there, 2.576. All right. Okay, so perfect. All right, 10. I'm not going to type, like I said, I'll just wait and do the homework. There it is set up formula-wise. Here it is entry. See, 0.99 is your sea level. Pretty straightforward. 87.26 and 98.74. The only challenge I anticipate with these problems is after we learn the next section is paying attention to whether you're using the Z interval part or the T interval part. That's going to really probably be the only challenge to this. And, oh, we still got, yeah. Let's look at this one. All right, so this one they give you the population standard deviation symbol, your little lowercase sigma. So that's another clue. We're doing it the same way. Pretty straightforward here. The 90%, well, there's 0.9 for 90%. 1.645 is the number off that chart. And then there's the answer right there, which rounded to 1 decimal place is answer D. Okay, here's kind of a conceptual question. They've been known to, I don't know, I might put this one on the third, something like, maybe I'll try to word it as clearly as possible. They've been known to sneak a question like this on the final. I think they're doing a departmental final this semester, so. But let's it's just kind of seeing if you understand the concept more than anything else. No calculation involved. Here's the confidence interval. So they took 250 students at this university and evaluated how many credit hours they were taking. And we want to interpret what this means. And let's see, 99% of the students take between those credit hours. No, this is not it's not a proportion. It's not measured that way. Where a proportion of people fit into a certain interval. Well, you can do confidence intervals for proportions, but that's not what this is all about here. Now, B is a little tricky. Let me jump down to D for a second. Well, D is a lot like A. They're almost kind of similar. That's not right either. The probability that someone's in that range, and that A student, that's not what we're measuring here. We're measuring a mean. That's the key. We're not measuring proportions, and we're not measuring the probability of a single student. We're measuring the average, the population average, all students. Does it fall in that interval? So let's look at B, and then we're going to see why C is right, because they're close. We are 99% confident that the average number of credit hours per quarter of the sampled students fall in the 13.793 to 14.607 hours interval. Well, that sounds pretty good, but that's not quite right, because actually we're 100% certain that the sample students falls in that interval, because we know what the sample mean is for those students. So remember, you're using a sample to make an inference about a population. So that's why that's not right. Here's the key why this one's right. We are 99% confident that the average number of credit hours per quarter for all students at the university falls in that interval. So we are using that 250 to estimate the mean of all students falling in that interval. That's the key. So that's why B is not right, because we know what the mean of the sample is. It's 14.2. But we're not 100% sure that the mean for all the students is 14.2. That's the key. But we're 99% sure it's in that interval. Okay, a little tricky. Okay, I wrote a little story about it right there. So, all right, let's jump over and see what kind of entertainment we can find in the homework here. Looks like it hadn't timed me out, so that's good. All right, let's see. Okay, assignment manager. Oh, I guess probably sometime later tonight, I'll cut off the second, or tomorrow, maybe the second batch of homework, and then I'll open them back up again. Probably about 3 weeks, 2, 3 weeks, but just, like we normally do to stay. Yeah, I was going to put a cutoff date and I just forgot. But no harm, it doesn't hurt anything that I didn't, but I just want people moving forward. Okay, let's see what we got here. I think it's going to be lots of fun. Okay, this basic kind of calculation there. So good practice, good starter problems. But as you know by now, I tend to always skip over those. I'm going to skip over this one. I want you to try it. This is very similar to that question we just talked about. Just talked about there at the end of the notes. Another one of those. Well, I may come back to one of those. I don't know. We'll see. But dang, do I have any calculations here? Or I'm gonna go back and I'll go back and look at maybe one of those other ones. But all right, this looks like a good one. I like it. All right, this one's good. Maybe something okay, it has lower than upper first. So I've just seen problems where it's maybe this is different. Maybe this is just what we used to use or something. But homework, maybe that won't come up. I'm just going to write something here on this page. But I've seen them before where it wrote, upper value. There was the box, and then lower value. So it could be a little tricky there, if it did it this way. I've seen that before. I mean, I wouldn't have just, that wasn't just in my imagination. I know I've seen that before. But evidently maybe it's not there anymore because it's different set of problems. Hopefully it wasn't on the last one, was it? Well, we don't know yet. All right, so now this one thing I don't like about this one is it should have told you population standard deviation, which I would absolutely make sure I did on an exam. However, since we are in the 8.1 homework, that kind of implies it's the population standard deviation. But obviously on an exam, I got to tell you which one. So that's the logic you can use here on this one, is that you can treat it as population because it's in that same section. Let's see. Okay, now let's see. We've got 99% confidence interval. So I'll just toggle back and forth here and enter everything I need. Stat, test. All right. Well, I stared at that standard deviation number enough to know that that was 100. Let's see, the mean is 320. Sample size is 64. Excuse me. I had that cough last week or two. Oh, thank goodness, only one decimal place, I guess, right? 287.8. Uh, 352.2. Yes. Now, I didn't mention this, and I maybe one day go back and add this back in the notes, but that's why I'm glad we're doing these. I don't really put this as a test type question, but let me. It's not a bad concept to know, though. The idea on this is that if the value they put in here, if you think you can claim that something's going to be a certain amount, which we're going to talk about that when we learn about hypothesis testing in the next units starting next week. But anyway, the number needs to fall in your interval. That's the key. So anytime somebody says you have the right to claim this or whatever, if the number's not in the interval, you say no. If it is, you can say yes. Manufacturer does not have the right. A mean of 370 is, standard errors. We talked about that last week. Standard error is it's just this part right here. That's the standard error. So for this one, the standard deviation was 100, and that was the square root of 64. 100 over 8 should be 12.5. That's the standard error. So let's see. We can rationalize this out. Above, let's see. Yeah, definitely above. That'll be above the sample mean. So we're comparing 370 to 320. 370 minus 320. And I'll just hit enter. Divided by that 1250 we just calculated. Okay, so they did this on purpose to make this work out exactly right. So it's 4 standard errors above the sample mean. So it's highly unlikely. I'd say extremely unlikely. Super duper unlikely. This can be a little tricky. Must you assume the population light bulb is normally distributed? You see it's got questions about the central limit theorem. If we know the population standard deviation, and when it says large enough, remember that term is kind of the central limit theorem meant 30 or more, is considered large enough. So let's see. Must you assume it's normally distributed? Let's see. This is confusing. The sample size is not large enough. It is large enough. Yeah. What am I? No, the original population. Excuse me. No, the original. It isn't one of the no's. It should be. This should be this. No, that's what I was. Because the original population does not have to be normally distributed because we have the n is more than 30. Maybe it's B then. All right, it's B. Oh, that's one I should have clicked to begin with. Never mind. Yeah, that's obviously right. But the large enough means being more than 30. Sorry about that. They're changing standard deviation to 84. No problem. Stat. Standard deviations. Coughing attack here. Get some cough drops. Ugh. So I'm assuming that nothing else changes here. And let's see what it wants here. One decimal place. 293.0. 347.05. 347.1. Excellent. All righty. Manufacturer. Let's see. I'm going to say, once again, I'm going to say does not have. How many standard errors this time? Let's see. Now the new 84, that's 84 divided by the square root of 64. Why would they pick a number that doesn't divide evenly here? Beyond me. 84 divided by 8. I don't like this problem. 10.5. How many standard deviations is that going to be? So it's 50 again. 370 minus 320. 50 divided by 10.5. More than 4. Above. Highly unlikely. Yay. All right. I don't know if I'm going to go back and do another one. I think it's time for a break.
Sorry, can you show us how to do number 6?
You want to take a look at number 6?
Yes.
Yeah. All right. We'll do 6 and then we'll do 6 and we'll go on break here, I think. So, yeah, I'll leave all those other ones there. You know, you can ask me individually later if you want to or something, but which is fine. Let's see. 1 gallon water bottles, standard deviation 0.01, 50 selected. Sample mean of a 1 gallon bottle is 998. Okay, so we should have everything we need here. Stat, test. That was 998. This was 99. I think that was 0.01, I think. 0.01, yeah, 50. Yeah, the one from the 1 gallon size bottles is not needed in the problem. Unless they're going to ask another one of those, how many standard errors above, or can you claim that it's accurate enough to say it's a 1 gallon bottle or not, in other words. But the number 1 itself is not used here. Five decimal places. Dang, they're not playing here, are they? They're using every one of them. 99478. Uh, 10012. What the? Did I type that in wrong? Got the low end right, but not the high end. You got to be kidding me. How's that not right?
Is the end supposed to be 64, or was that different?
Oh, good catch. But I'm surprised. I'm shocked it didn't mess it up the first time. No, good catch. It's 50. But dang, then why was the low end right? Oh, it waited for me to do the whole thing. That's right. The whole thing is wrong. That's why. It didn't judge it just on the low end. It judged it in the whole thing. 99436. Well, I'm glad that I did it wrong versus this wasn't going to be like an issue with the problem itself. Yeah, that would have been a mess. Now I give up. No, I don't. Did I type it wrong? 99436 1.0016. Yeah, you were definitely right about the end. Do I need to add a 0 to this? Oh, goodness gracious. This might require a manual calculation. Well, you still use a calculator, but you got to be kidding me. Because the calculator is not going to give us, it's only going to give us the number of decimal places it gives us. That's pretty rude. So let me do it as I hate to get rid of that problem because it's there's not that many calculation problems in there, but I guess I could ditch it. I don't know if it'll let me add something or not, but I wouldn't mind adding a new one in there to replace it, but that's pretty rude. I don't know. I may have to call a board on this mission and deal with it later because I'm wasting too much time on this. Let me try it manually here. 998 plus. I'll use 2.576, but I might have to get more accurate than that. $50 divided by the square root of 0.01. are they using 5 decimal places? Sometimes this, my stat lab really irritates me. Where am I? Oh, ha! Oh, see, I'm nervous about wasting time here. I can't even pay attention to what I'm typing. It's 0.01 divided by square root of 50. I'll reverse the numbers. There's the 4. 100164. It's not supposed to, shouldn't have to do it that way, but I guess you're going to have to for that one. Certainly won't have to in an exam.
Professor, I was able to do the same question using the TI-84, but
with different numbers?
it's different numbers, but the 5 digits came out after the decimal, so I don't know.
How did I only, but you saw what I got though, right?
Yeah, it looks like you were short a number, right? So I'm not sure why.
Well, maybe is there a way I can make it display more? I think it shows only what it fits. Yours showed another number after that?
Yeah, it showed the 5th, but it was like 0.99864. I didn't have 1. It wasn't greater than 1. It was just it was less than 1.
Oh, so it might be dependent upon the numbers that come in there, right?
Yeah, maybe so.
Yeah, that's what it sounds like to me. Are they right to complain? No, because the 1 gallon fits in that interval. Well, now we know. Must you assume it's normally distributed? That's pretty much the same answer as the other one. 90%. Oh, great. We're going to whiff this again now. Let's see. Well, oh, I don't need a second there. Let's see if this works. 90%. All right. Oh, this is probably not going to work. That number on the right is probably going to be 99567. And 1.000. I'll add a 0 after it. None of that's going to matter, but of course not. But if I do this, and then do that with a minus, I'll just leave it plus. Actually, I'll change it to minus. And then do it with plus. Well, the good news, this is not going to be an issue for exam purposes. Because all you got to do is pick the right answer. Looks like 9, there it's that upper number again, isn't it? I was just going to pick some random number. I'm not saying I would have picked 2, or 3, but I was just going to stick a number just to go ahead and make it wrong, and move on. But it looks like I can get it right now by putting a 3 there. They just didn't have the stupid 5 decimal places. What are they thinking? Look at that, see? Still in there. Still does not have a right to complain. All right. Good news, the next section, even though it's a different distribution, it's still confidence interval, so we don't have to re-explain the whole concept again. We'll be able to jump right in and explain the new part of it here. So, all right, I think my brain needs a break here. All right, I'll be back in about 10 minutes. I'll bring up the new notes if you want to see them. So, all righty, I'm back. I found some Delsum cough syrup that might help me here. It may not kick in by the time this class is over. I didn't have any cough drops. That'll be on my list to do for tomorrow. Go get some cough drops. All righty. Let's see. Confidence intervals for the mean. Population standard deviation unknown. So that means we're either just say the word sample standard deviation, or just has to give you the S, little s. So we can do it symbolically, and that'll be fine. That's T distribution. Comes about, when this came about, this guy back in the 1800s, I think, Gossett, he published under the name Student. That was smaller, the unknown standard deviation, especially smaller sample sizes, the distributions weren't always exactly normal, and came up with this. All I think is kind of funny is that guy. Let's see if I can bring him. He was a statistician for Guinness Brewery. So maybe he had been drinking product all day or something like that, and it came to him or something. I don't know. He probably wasn't a taste tester. Guinness Brewery. Always find that amusing. There it is. Chief brewer, but mathematician. All right. So you never know where you might find mathematician people, mathematics kind of people. You wouldn't think a brewery would need one, but all right. Anyway. Now the T distribution is similar to the normals, that it's continuous and bell-shaped. But the difference is, and that's where it came in, the issue with not knowing the population standard deviation, mostly smaller sample sizes, is it has a slightly different shape depending upon the sample size. It's not all just one universal distribution like the regular normal distribution. That's why they say there's a family of distributions, and they differ. Standard deviations differ due to the sample size n. And it kind of actually, now you're not going to have to worry about getting into all this kind of stuff here. I don't think you're even going to need this inverse T function. I mentioned here it's not even in the 83. You probably really aren't going to need it anyway. but if somebody wanted to use it, they could. And as you see, the top one is supposed to be the, I'll talk about this DF here in a minute, but you see the red one's a t-distribution, the blue one's a t-distribution. And what happens is as the sample size increases and gets larger and larger, the t eventually becomes the normal distribution. It all merges into one thing. But for smaller samples, it's actually a little bit different. So what's going to happen is that you're going to have critical values here. What is this one for? 95%. So when we're doing a normal distribution, I mean a confidence interval using the normal distribution with standard deviation known, population known, for 95%, it was, that critical number was going to be 1.96, as it's labeled right here. Always, whether if n was 30, 50, 170, whatever, always 1.96. But here, it's different. It's based on whatever the value of n is. Because if the shape of the graph is different, therefore the 95% marks are going to be different. So that, you know, it's essentially moving. So now for this to work though, the original data has to be normally distributed. Otherwise this will not work. So you might see that sometimes in a homework if it says, maybe it does, I know it, once again, I know it has in the past, but it may say, you know, what assumption must be made here? And that the population of the random variables normally distributed. That wasn't true in the last section. It didn't have to be, because the sample size was more than 30 and we knew the population standard deviation. That's where the central limit theorem was kicking in. But here, the original data must be normally distributed or this is completely irrelevant. And we don't know the population standard deviation. We have S. Now here's what that DF stands for. Stands for degrees of freedom. It's a real simple calculation. It's just n minus 1. So you'll be always given your n. So if n is 20, degrees of freedom will be 19. There's a whole page down here. I mentioned it's not going to be tested on here or whatever. And I'm not going to go through all this in too much detail, but just kind of show you one example here. Like this equation right here, x plus y plus z equals 15. And let's say you choose a value, I don't know, 6 for x. And then I choose 2 for y. Well, if x plus y plus z equals 15, I can't choose for z. I have to calculate what z has to be, because it can't be just chosen if x and y are already chosen. So 6 plus 2 is 8. That means z has to be 7, which makes it 15. So in this case, there were 3 variables, but 2 degrees of freedom, because you had 2 choices, freedom to choose 2, basically, or whatever. So, and it gets even way more involved than this. But you, fortunately, you don't have to worry about it. But that's what is sort of in a simplistic terminology kind of means or whatever. That's what the freedom of choice is. And then the other one would be, you wouldn't have the freedom of choice. And if you want to just read through that for fun, you know, go right ahead. But none of that's directly on the test or anything. So. Okay. That's very important when you're using this chart. And sometimes I'll probably ask a question on test where, when you do the confidence intervals, you won't have to get these numbers off the chart, but you may have a question where it's just getting the number off the chart. So you will want to know how to read this, even if you aren't using it all the time. Now this one-tail, two-tail stuff, that's going to be used in the next unit, hypothesis testing, all off this same chart. But this week, we're only using confidence level. Okay. So the degrees of freedom, now that's where we get our degrees of freedom. So that means if we know our confidence level, we don't automatically know what the critical value is going to be until we know what the degrees of freedom is. So now we got to, so instead of just working in this top row like we do for the Z, we have to go to the proper row that represents the degrees of freedom. I'm not going to read all that. I suggest that you look at it, but I'm just mentioning here, like for the T-chart in my notes goes more pages than this, but on the test, because usually it's smaller samples, well, it doesn't really matter. You're using whatever you want. I keep forgetting about that. But if this was an in-person exam, I would only give this page of the chart because I would make sure everything fit, on that chart. But you can actually investigate the chart further because you'll have access to it. So, but anyway, so you can read through that, and if it's not totally clear, don't worry too much about it. But so this is talking about how to find the critical values off the chart. Yeah, I don't know if it's even worth. There's the way to do it in the calculator. Like I said, the 83 folks can't do it because then inverse T did not show up until the 84. So if you're using an 83, it's not even an option. So, but even if you are using an 84 higher, I don't know if it really benefits you that much. Because for T, I'm not using anything that's not on the chart. Like the last section, we did a weird percentage, like 82%. That means people that they're just using the normal chart could still get that without technology. This would not be fair because everyone would have to have technology to do this. So that's why everything we do here is going to be off the chart. 98%, N is 13. So if N is 13, degrees of freedom will be 13 minus 1. That's usually 12. So let's go here. 98%. 12 degrees of freedom. Maybe I'll just highlight it here. And 12 right there in the middle. Oh, wrong row. Right there. 2.6810. Go. Ta-da! Now, one thing I'll mention here, and the same rule kind of applies to the next one or any of them, is on an exam, because really this is not that difficult. So really the only way I can kind of make this challenging is to have an answer choice that has the answer below, meaning you forgot to subtract 1. Because really there's no challenge. The only challenge is remembering to subtract 1. So I got to at least put something there to, keep it honest. So you'd probably see that one in blue as a choice, but the yellow one is the correct one. So long as you're careful, you just remember to subtract 1, you've mastered it. 80%, N is 24. 80% is column 2. N is 24 means 23 degrees of freedom. 1.3195. Ta-da! Okay. That way we've already gone through the concept of how confidence intervals work, so I don't need to explain anything other than the difference here is instead of Z alpha over 2, it's now T alpha over 2. Instead of the numerator being the sigma for the population standard deviation, it's S for sample standard deviation. So the theory of how it's calculated is still exactly the same. Okay. So I don't have to go through all that again. Of course, the part to the right, this is still the margin of error for this one. Here's one where it's asking you to find the margin of error. I could actually ask the margin of error on a test. I'll tell you how you can kind of do it in the calculator. There's not a direct calculation for it, but I'll show you how to do it. Let's see. I could just do it for this one, actually. Well, I'll go ahead and do it the way I set it up, and then I'll show you real quick. If you're doing the calculator, you can skip this. Random sample of 7 computers. Sometimes people fuss at me whenever numbers are written as words. I mean, what's in? 7 right there. I don't like that. I want it to be a number. You'll be all right, though. It's not like these questions are going to be 30-page documents or anything, so I think you'll find it. Mean repair cost is 100, standard deviation 4250. Assume the net variable is normally distributed. That's what I was saying earlier, to even use the t distribution. It has to be normally distributed. Now, this one is, in this case, it doesn't have to say the word sample. Might be better if it did. I'll keep that in mind when I'm designing test questions. But because it's part of the same sentence saying that it's from a random sample, that kind of implies then that's going to be a sample standard deviation. But it probably would be better if I put the word sample or used S in there or whatever. I'm not trying to trick you into thinking that it was the population standard deviation. So I would probably put the word sample in there just to make sure. But that's the logic on this one, why I could get away with it not being there. Okay, so the margin of error is the part to the right of the confidence interval. So I'll do this one in the calculator also. And some of the other ones I might not, because we're going to do homework again. So 7, N is 7. So N is 7. This means 6 degrees of freedom. 95%, 6 degrees of freedom is, how about right there? In the 95 column, 6 degrees of freedom row, 2.4469. I keep bringing the wrong one up there. 24469. So the margin of error just becomes 2.4469 times the standard deviation of 4250 divided by the square root of 7. Notice that this formula is the square root of n, because this is often a commonly asked question. You don't subtract 1 there. That's only for looking up the number on the chart. You would still use the original 7 right there. So that's a common question, so I always try to preempt it by just addressing it. So that's supposed to be 7. I get 39.31. So then I can go 100. The mean is 100 minus 39.31. And then go mean is 100 plus 39.31. There's your interval. Let's put this in the calculator. Stat. Test. So now we have another choice. So now it's not automatic. We have to realize it is t interval this time. That's very important. We'll give you the wrong answer. Well, unless n is really large. Like I said, because if n is large enough, their t and z are the same thing. But for this one, it'd give a way different answer. And you could check it yourself later if you want to call me out on that one. But for 7, I promise it's going to be different. 4250. Yeah, that would be more than just a rounding situation, I promise you. 7, and it was 90. Crap, I forgot. 95. Make sure everything else is okay. 4250, yeah. What? What went wrong here? 100, 42.5, N is 7. I must have picked, did I pick the wrong confidence level? That's the only thing that might be wrong. Yep. I didn't change it to 9.5. In my head I did, but I didn't do it actually in the calculator. There we go. That's the answer. Now, if a question was asking you the confidence interval, now as long as it gave you the mean, that's the key. You'd have to have the mean. You could do the confidence interval, subtract the two numbers, and divide by 2 to get your margin of error. But if it didn't get the mean, you'd need to do it by using the formula right here. Because obviously, you know what though? Actually, you could make up a mean and it wouldn't matter. Yeah, you know what? You could just put anything in there for the mean. Because remember, the mean just sits there in the middle. The margin of error is not a, yeah, you could do a confidence interval. If it's only asking for margin of error, obviously to do a confidence interval, you have to have the correct mean. But you could just make up a number for the mean and you'd still get that same margin of error. Yeah, that would work. Well, another reason I was mentioning, I say the answer would be significantly different. If this had been a problem involving the last section with z's, that 2.4469 would have been 1.96 because that would have been the 95% level for z. So you see that throws it way off right there. I'm gonna go back to that chart for a second. I only have one page of the chart, but anyway. Now, if you look at those t-values, I'll pick the 95% column, 1.96. We'll go down that column. You see they're all decreasing the farther down you go. Some people put the infinity at the end, which sort of makes sense, but I want to move the infinity there to the top row so it'd be easier for people to use for the z. But look, you see how it's decreasing? So if I showed more pages, in other words, it's working its way towards 1.96. All right, grocery bill. So now it's just distinguishing T or Z. But now in this section, we know they're going to be T's, but that'll be the only thing that challenge on the test is whether it's a T or Z. 17 shoppers. And my rule of thumb is not, I usually use smaller sample sizes whenever it's, the homework may not, but whenever it's going to be a T, I generally use less than 30. That's just what I usually do. 17 means 5380, standard deviations 1840, 80% confidence interval for the population mean. So here it is using the formula. If n equals 17, that means we have 16 degrees of freedom, 80%. Second column, 16 degrees of freedom. Right there, 1.3368. But if you're doing it in the calculator, you don't care about any of this. I'm just showing it. There it is using the formula. I'll kind of skip right through that because I think we determined that the regular crowd here is pretty much using TIs here. So, but I'm just going to look at that for people looking at this later. But there's the formula, and they can always contact me if they're having any issues or anything. Oh yeah, we can do this one. Okay, I'll put it in there real quick. Stat. Test number 8, T interval. So like I said, be super duper careful here. Is it warning me? All right, back to 5380, 1840. 5380. 80, 1840. And is 17. And notice it says, assume the bills are normally distributed. In other words, that's just the key phrase, meaning that, well, we would still have to do it this way, even if it didn't say that, because we have no other options. But in theory, it kind of needs to be there to really make it valid. 80%. So if I forgot to say it on a test or something, you would still treat it as if it was there. $47.84 and 59.77. How'd we do? I got 8.3 here, but that's just slight rounding. Yeah, there we go. Ta-da! All right. I'll just look ahead and see what we got here. I don't have to do every one of these. I definitely want to do one with the data there, but I may skip over these, some of these. Oh, we did the chicken one real quick here. I circled that. There's another one where it gave a word as a number. 12 chicken eggs. How about that? 193 sample mean. There's your S right there. That gives it away. Okay, this one's a little different. It says it up here. Of course, obviously, you don't have test questions that ever look like this, you know, but it does say up here normal distribution. That should be in the question, but that's just from a test bank where it just has that description in front of a block of the same type of questions. So I never have question blocks, so they're all independent. Okay, let's see what we have here. I think we can do this. There it is using the formula. I can do the chart real quick. 95, it's N is 12, so it's 11 degrees of freedom. 95, 11 degrees of freedom, 2.2010. So there's where that came from. It's pretty straightforward using the formula. Pretty straightforward as long as you pick T interval. But 193. 15.4. 12. I think it's, I won't hit enter. I won't hit enter until I check. Is it 95? Yeah. One 18322 20278. How'd we do? Love it. I'm not saying this is going to happen for sure, but you know what could happen on a test question. I pick these questions. Sometimes they do it. I don't do it on purpose, but sometimes they'll do it where the answer is there if you did it as a Z interval. So that just, so you might, if you did the wrong interval, you might think you got it right and you really didn't. But I don't know. I can't say that's going to happen, but I can't say it's not going to happen either, though. So let's see. Oh, this was one where that happened, actually. This problem I got here, I'm not going to work this one out, but that I did it as a Z interval. No, I guess not. Yeah. Yeah, if you did it as a Z interval, you would get answer D. But the correct answer is E. Yeah, that was ones. I don't know, but I'm saying that could happen. Okay. Let's see. What do we got here? 27, 99%. So 27 means 26 degrees of freedom. What is it? I keep forgetting the percentage. 99. 99 and 26 should be right there. 27787. I'm not even going to type this one in so I can move on. So we can type in the next one. But obviously you can see the result. So you could, if you typed it in yourself, you know what you're looking for. But then I also have it set up correctly this way too. So there's what we're looking for if you do it in calculator. But let's do this next one since I don't have the work. I always say show the work in class. I'm gonna show this one though, only calculator. I mean, I could do it. I could write it out per request, but I mean, unless somebody wants to see it, but not, I'll just put it in the calculator. All right, 13 hotels. Yeah, notice that you don't even, when you're putting it in the calculator, you don't have to even think about the degrees of freedom. You just tell it what n is, and it takes care of the rest. So 172.10. And standard deviation is 2390. Don't need that. N is 13. Confidence level was 99. So let's see if that's the answer I had marked right there. 151.85, 192.35. Beautiful. Okay. Here's one, a UHD GPA one. But I'm really interested in getting to this next one here as much as anything. That next one's is key. This one's pretty much just straightforward entry again. Let's see, but I'll put this one in there real quick so you can see it. Well, actually, you can see the end. You can see everything to enter right there. I think it becomes kind of redundant at this point. I don't know. Especially when the ones you can kind of see it right there, right? Now here, the smaller sample, I don't know, maybe this, I can't say for sure yet, yes or no, whether I'll do this on a test or not. I don't know, but I think it might be in the homework. Might not, because I don't want people that aren't using a calculator to have to go through a bunch of extra trouble, which they would. Like they use it if they're not using the TI. This one's a little bit rude, so I probably would not put it on the test, but this might be in the homework, but certainly worth looking at. Is when they just give you the actual data instead of giving you the sample mean, the sample standard deviation. which implies they want us to figure out the sample mean and the standard deviation. It's our job to calculate that. So without actually going through all the detailed steps that won't apply to you unless you had to do it this way, is this involves just taking formulas from early the semester and calculating, well, the mean's easy enough, but then the standard, using this formula earlier in the semester for, well, heck, even someone could do this in Excel quick enough, couldn't they? Yeah, what am I saying? You could use Excel, so I could give this problem, because all you go, yeah, you can just use stdev.s, right? And then average for the other one. But even then, if you're using a TI, you don't even need to go through that much trouble. So this would not be that cumbersome then, or whatever, because somebody could use Excel. But anyway, I got the mean, I got the standard deviation, and then it was the n was 5 because there's 5 numbers. So I found this number on the chart: 90%, 4 degrees of freedom, 2.132. That might have been when I used to use a chart that only had 3 decimals instead of 4. Unless the last number here was a 0. I never have changed that. Maybe it's not. Okay, 2.1318. Yeah, that's from an old, when I used to use an older chart. It's not wrong, but this one's a smidge more accurate. It's got 4 decimal places, but I mean, it doesn't kill the problem. But anyway, no harm. Maybe I'll change that thing. And then you would just plug it right into the formula. Once you have the chart, you have the mean. So you see, it's a lot of extra work, but even using Excel, it's not. But here's how you can do this entire problem in 1 step in the calculator. Well, 2 steps. You got to do a list first. Stat, edit. We haven't done the list in a while. And let me see my numbers here. Wait. I haven't done a list. What are they? 2, 3, 4, 7, 9. Oh, same number of values, so I don't have to even delete that list. Remember the rule, anytime you're typing as equal or more numbers you're about to type in, you don't have to clear the list. Obviously, if you're doing less numbers, you want to clear it so you don't have numbers in there that you don't use. All right, so I'm going to quit out of that. We're not using any commands. We're not using the 1-bar stats on this. We're going to let the t-interval take care of the whole thing by doing the following. T-interval, we're going to choose data this time instead of stats. Data means it's going to be looking for a list. And the default place it looks for any list, if it wasn't there, you would have to change it. But L1, that's why I try to put everything in L1. Whatever that frequency number means, that just needs to be a 1. You just leave that alone. And it was a 90% confidence interval. So in other words, now it's going to take that data, calculate the mean, standard deviation, and the entire confidence interval. Ta-da! And that's what I had doing it the long, gruesome way. 2.22, 7.78. There it is. Wasn't that fun? Oh, yeah, and there's that page we talked about, the meaning of the degrees of freedom. So, all right, that takes care of that. So let's jump over. Let's get rid of this homework. While I'm thinking about it, let me bring up something real quick from a previous homework. Was it the last homework we did? Or was it the one before? I'll check. I'll know the problem when I see it. It might have been this one. Let me show the completed problem. It's got to be this section, I think. It's at the end. I know that one of the last two. No, it was the percentiles. I think it was the percentile homework. Let me bring up 6.2 at the end of that section. Let me just go right to number 6, or go flip ahead. This is going to either be the last one or the next to the last one. Dang, I can't figure out. Maybe I missed it in the last one there or whatever. Let me look at problem 5 again. Wait, let me scroll down and see the rest of this problem. Dang it. I should never have brought this up if I didn't know exactly where it was. But it was a problem that we did last week, actually, that can be done differently now. Maybe I should go back a couple of problems here. Maybe dang, I don't know. Thought it was, but it was a problem where I calculated. God, I have to watch my video again, but I calculated. I said you have to calculate this amount, and you have to calculate the lower amount, and subtract them, or something or another. But anyway, it was actually set up perfectly as a confidence interval, but we didn't know confidence intervals at that time, and I can't remember without looking at the video which. But I thought I would see it right here. It sort of looks like D, but D is the outer ends. I'm going to have to, maybe I should run through 7.2 again. I didn't look at 7.2 carefully enough. Because actually it was a problem, like I said, it was a problem that could have been done easily with a confidence interval, but I couldn't really explain that at that point in time. All right, let me slow down through these real quick. Because maybe I didn't read these other ones before. Yeah, this is it. This is it. 7.2, problem 3. Yeah, this is the one where I explained how to do this one, and you had to figure out what the lower percentile, upper percentile. But you know what? Because it says 61% between what two values, you can do this because it's population. That could have been just done with a Z interval of 61% confidence level Z interval. But I couldn't really say that at the time. But I had to explain a workaround on that for that problem. But yeah, okay. Sorry. Okay, that would have been done with. All right. Okay, straight up. These are just looking up values on the chart. They've got a chart here, but I don't know. People have told me they like the one I did better because it might be. I think it's a little trickier because it's the way they define it's trickier. Yeah, the cumulative probabilities and the upper tailed areas, that makes it hard to figure out what you're looking for. Mine's much easier because it's just straight out says confidence interval. But my chart goes a few pages. So you can find these values for 37. Well, actually, they'll be 36, which degrees of freedom, and 56. So it's just, yeah, it just wants the critical value. Like I'll do the first one. 99%, 36 degrees of freedom. So I need to bring up the entire, well, maybe let's see, I might already have the entire chart up. Yeah. So 36 degrees of freedom. And it was 99%, I think. So it should be 2.7195. It would take me too long to explain how to interpret that chart. I can do it, but it would take too long to explain and just probably put you in worse shape. When you know you can just use that one that I have. They're trying to be helpful by providing you a link to the chart, but they're not being that helpful. There we go. I mean, I don't mean to say that from like an egotistical point of view, but mine is easier to read, easier to follow. Let's see. So there we go. So it's a matter of looking them up on the chart. Easy peasy. We skip through that. Yes, I want to leave this question. Yeah. Knew that was coming, didn't we? Okay, this could be good. This could be good. I'm just kind of sniffing around here to see what we're going to do. Sure, we're going to do a couple of these. Oh yeah, here's one with data. Now you know what? We can start with this one. I'm almost tempted, and now you do whatever you want. I'm almost tempted to get the mean and standard deviation from Excel and then just use the stats feature in the calculator and type it in. Or you can type all those in the calculator. You kind of got two ways to go here. All right, so one way is to do like I just showed you. Put those numbers, it's because of decimal places. It takes longer to type numbers with decimal places. But if that's the way you want to do it, then do it, because it's a great way to do it, technique-wise. This isn't bad either. So I'll just show you this way as an alternative. It'll be less typing if Excel will ever wake up here. Come on, Excel, you can do it. Come on, give it to me here. Jeez. Guess I should have already had it open. I didn't think I was necessarily going to need it, but I guess in this class it shouldn't be a surprise. All right, let's go. Well, theoretically, this should have been a good way to do it. Now you're probably thinking, dang, I could have typed them in the calculator by now. Oh, maybe your Excel will be opened up quicker than mine was. Well, there they are in all their glory. So I'm just going to come over here. What is it? A1 to A15, wherever, equals AVRAG, A1, A15. And then I'll do equal STDEV dot S. Okay. Now, then I'm going to do this. I'm going to go calculator. So if you're doing the way by entering the data into here, the calculator, you'll want to leave it like this. You'll want data. But we're going to manually enter the mean and standard deviation, so we want this to be back over at stats. So typing in the data, you'd stay with data. Well, that's the values from the other data. Oh, what do we want here? 7.084. Now we just have to decide here. Our rounding, I don't know. I'll give it 4. 1.403 is probably good enough, but I'll go 1.4029. Just to try to make the stupid MyMathLab happy. Probably would have been fine, but I'll take that extra decimal just to be sure. And then now we got to see, got to go back to find the problem, as I don't remember the confidence level. 95%. So that's all we need. Oh, N. There were 15 numbers there. So obviously didn't tell us N. When it gives you the numbers, you're supposed to count them. 15 numbers, 95%. Here we go. Two decimal places. 6.31. 7.86. There we go. So there's your choice on how you do that. Interpret. All right. B is wrong. D is nonsense. A or C? A. We're concluding that 95% confidence that the population mean will fit in that sample. Yeah, because C is referring to the amount for the sample. That goes back into that other problem with the credit hours thing we did before in the last section. Yeah, we know the sample's in the interval, but we're doing it to estimate the population. Yay. Yeah, here we go. So when this pops up, you just check that, whatever answer choice, wherever you see that answer, because that's going to be the answer every time. Remember, I said that's the assumption. It's normally distributed, so is valid. Let me see what, I don't know. Let me read the, ooh, this one's tricky. Do you think the assumption is needed? Oh, the assumption is needed. Yes, it's definitely needed, or is reasonable. For n equals 15, should be this. Since no, well, ooh. I wouldn't think the sample size less than 30 would be the reason. I thought it would have the normally distributed thing here again. Let's see, let me read this again. I mean, it's definitely needed, but the reasoning doesn't make sense here. Oh yeah, it's sample size is okay. I was reading it the wrong way. Hopefully it'll be this. Nope. It has to do with the plot. Well, this question is weird. I didn't read. I should have read that thing a little bit more carefully. Well, that's a bunch of nonsense. Now you know. just pick that and move on. No way will that kind of nonsense be on a test. It could have stopped just with assume the population was normally distributed. All right, let's see if we can knock out at least one more, maybe two more of these if they're not too many confusing parts to them here. Oh, I don't know. Don't know what anything's. Actually, I could look at all the pieces to see what looks. That one looks kind of quick. We could probably do that one pretty quick. And then that way pencil and get another one. All right, not too many parts to these, right? We can do this one, I guess. Graded 200 tread wear, sample N is 25. Okay, once again, like I said on a test, I would make sure that, well, it does say sample standard deviation, which is good, but it should probably also say assume the population is normally distributed. But you're actually okay with the sample standard deviation. Let's see. Okay. All right, 197.4. All right. 97.4. Ba-ba-dum-bum-bum-bum. Standard deviation, 23.6. $25. And 95%. $187.66. All right, and 207.14. Let's see how we did here. Tremendous. All right, should we accuse them of producing tires that do not meet performance? No, because the 200's in the interval, so even though the sample mean is 197.4, there's a 95% that the actual population mean is in this interval, so which does contain the 200. So I like it. Well, we know this one's probably going to be A, right? We just saw it, but the number of standard deviations is essentially the z-score. But you probably got to calculate this as the z-score for, X bar, which you may recall from last week was so it was the sample mean was 190. Oh, above the confidence interval. Oh, that's okay. So that's what we have to use. Tread wear index. Okay. No, we still calculate it as the population mean. Sample mean 197.4. So it would be 211 minus 207.14, 3.86. Oh, wait, let's see, 211. No, it's not in there. Oh. 0.58 standard deviations. I must be thinking of this wrong. Okay, I'm probably overthinking this a little bit. I don't know. So 211 minus 207.14. .14 divided by 23.6, but I bet you it's divided by the square root of n. Ah, got it backwards there. Second square root of what was n? 25. And 0.58. And I got 0.82. What am I missing here? I don't know. Sample mean. I used the upper limit of the confidence interval. All right, I got it now. The first one did say confidence interval. This second number should be sample mean. Yeah, there's no chance that this is going to be on a test either. Now I should be able to divide by the exact same thing. No, I give up. I have to think. Maybe I'll think more about this later. My brain's fried here or something. I don't know what. I'd have to sit here when I'm not talking and write this out and think it more carefully. I could always address it next time or something, but come up with a logical reason for that one. Why it's that specific number. I'll knock this one out real quick and that's it. Random sample of 50 nonprofits, mean, standard deviation, parts A and B, 90%. All right, she should be straight up 90% T interval. So I can't even pick the right choice anymore here. 8. $50, mean was 33. Skip over to 50, then hop back up to whatever that is. Standard deviation 8, and it's a 90%. 0.90. Let's see how many decimals it wants. 2, so I'll go 31.10. And 34.90. Tremendous. Let's see. Quality improvement team coming. I'm looking at D. Let's see. Yeah, A is kind of tricky. It almost looks right, but remember that the population mean, the sample mean is the midpoint of the interval. The sample mean, not the, so that's the, by some fluke, the sample mean could equal the population mean, but it just means contained within the interval. 90% chance it fits in there somewhere. Yay! All right, well, I think I brain farted my way enough through that, so I think we'll officially close up shop for today, and then as far as lecture goes, you'll be seeing an announcement pretty soon about the little Excel assignment, which won't be too bad at all. You shouldn't find it too difficult. I don't even mind. It's too late now, but next week I'll even take a look at it with you, and discuss it. But so I think we got about 2 more weeks of lecture to cover the material. And then that last week can just sort of be probably a Q&A or whatever you want to do kind of thing. So actually we may have a couple of, well, yeah, that might be like a prep, Q&A for exam 3 or something or whatever, whatever you want to do. So but it should only take me a couple more weeks to get through this. So, all right. So with that being said, I'll officially stop the lecture now, and